Hello, everyone. Today, we'll discuss two fascinating concepts in logic and set theory: Cantor's theorem and cardinality. By the end of this discussion, you'll understand what these concepts mean, their significance, and how they apply in mathematics. Let's start with the basics. What is cardinality?
What is cardinality? Cardinality refers to the size or numbers of elements in a set. It's a fundamental concept in a set theory that allows us to compare sets in terms of their sizes, and it applies to both finite and infinite sets. Cardinality of finite sets. For finite sets, cardinality is straightforward. The cardinality of a set is simply the number of elements in it. For example, set A is equal to 1, 2, and 3. The cardinality of A is 3 because it contains 3 elements, which is the 1, 2, and the 3. Set B is equal to apple, banana, cherry, and manga. Ayan. The cardinality of B is 4 because it has 4 distinct elements. Notation. The cardinality of set S is denoted by the absolute value of S. So, for the set A, we write absolute value of A is equal to 3.
Today, we'll explore two types of infinite sets: countable infinite sets and uncountable infinite sets. While both types are infinite, they differ significantly in terms of their cardinality or the size of the infinity. First is the countable infinite sets. A set is called countable infinite if its element can be put into one-to-one correspondence with the natural numbers. Essentially, even though the set is infinite, we can count the element in some way. For example, the set of natural number. The most classic example of a countable infinite set is the set of natural number: 1, 2, 3, 4, 5, and so on. We can clearly match each number with itself: 1 with 1, 2 with 2, 3 with 3, and so on. This shows that we can count the elements of this set, and it has a cardinality of natural number, which is the smallest form of infinity.
Great example. But not all infinite sets are the same size. This is where Cantor's theorem comes in. George Cantor proved that the set of real numbers is larger than the set of natural numbers. Let's break this down step by step. To further illustrate this, let's consider a simpler finite example. Imagine a set S equal to the set of AB. The power set P of S would then be the set of a null set of A, set of B, and the set of A, B. Notice that S has two elements, while P of S has four. This demonstrates that even for a small, finite set, the power set always contains more elements. Now, extend this concept to infinite sets like the natural numbers. The difference in cardinality becomes even more profound, illustrating the existence of different sizes of infinity.
Cantor's theorem is a fundamental result in set theory, named after the mathematician George Cantor. It addresses the size of sets, particularly infinite sets, and introduces a surprising and important distinction between different types of infinity. Cantor's theorem states the cardinality of the power set of any set is strictly greater than the cardinality of the set itself. In simpler terms, if we have a set S, the set of all possible subsets of S, called the power set, denoted as P of S, always has more elements than the S itself. We're going now to discuss the key concepts. Before diving into the proof and implications, let's review a few key concepts. Cardinality. Cardinality refers to the size of a set. For finite sets, cardinality is just the number of elements. But for infinite sets, cardinality becomes more nuanced. Power set. The power set of set S is the set of all possible subsets of S, including the empty set and S itself.
Argument. To understand this for infinite set, Cantor used the diagonalization argument. He showed that there is no one-to-one correspondence between n or between and imagine listing all real numbers as infinitesimal expansions. Cantor's instructed a new number by changing the diagonal digits, ensuring it differs from every numbers on the list. This proves is uncountable and has a greater cardinality than.
Here's another example. Consider the set of natural numbers 1, 2, 3, 4, 5, and so on. This set is countable because its element can be listed in a sequence, where you can match each natural number with a unique position in the list. In other words, for any elements in the set, you can assign a specific finite number to it. This is what we call a countable infinite set. However, let's look to the set of real numbers, which includes numbers like pi, square root of 2, and even decimals like 0.123456789. Unlike the natural numbers, you can't list all the real numbers in a sequence because there are infinitely many real numbers between any two natural numbers. As shown by Cantor's argument, no matter how you try to create a list of real numbers, there will always be some real numbers missing from the list. This is because between any two real numbers, you can always find another real number, making it impossible to cover the entire set. Cantor demonstrated that the real numbers are uncountable infinity. This means that although both the natural numbers and the real numbers are infinite, the real numbers have a higher level of infinity. Their cardinality is strictly greater than that of the natural number. The cardinality of the set of natural number is denoted aleph null, while the cardinality of the set of real numbers is denoted C, and it is uncountably infinite. This difference in cardinality shows that not all infinities are the same size, and Cantor's argument helped establish the concept of different levels of infinity in set theory.
So why is this important? Cantor's theorem helps us understand the structure of mathematics and the hierarchy of infinities. It shows us that infinity isn't a monolithic concept, but something that can be categorized in different sizes. This insight has far reaching implications in many fields of mathematics and beyond. In computer science, for example, it's crucial when dealing with data storage, algorithms, and decision problems. Understanding the size of different infinities helps in categorizing problems based on their complexity. In physics, Cantor's ideas have been applied in quantum mechanics, where the concept of infinite states plays a significant role in explaining phenomena at the microscopic level. Cantor's work also carries philosophical implications. It challenges our classical views of infinity and forces us to reconsider our understanding of the infinite in the context of reality. It leads to more nuanced discussions about the infinite, whether in terms of time, space, or the universe itself.
To summarize, cardinality measures the size of sets. While all finite sets are easy to compare, infinite sets can have different sizes. Cantor's theorem shows that the power of any set is always larger than the set itself, and this idea reveals the distinction between countable and uncountable infinites.
Thank you for joining us today. We truly hope this discussion has provided a deeper understanding of Cantor's theorem and cardinality. These concepts can seem abstract at first, but as we explored, they are fundamental in understanding the structure of mathematics, especially when it comes to infinity. Cantor's work has far reaching implications, not just in mathematics, but in fields like computer science, physics, and philosophy. We encourage you to continue exploring these ideas as they help us comprehend not only mathematical theory, but also the nature of the infinite and how it applies to the real world. If you have any questions or would like to dive deeper into set theory or any related topics, please feel free to reach out. We're always happy to discuss further or provide more resources to help you grasp these fascinating concepts. Remember, set theory is a building block for many areas in mathematics, and there's always more to learn and explore. Thank you once again for your attention and participation. See you next time and keep exploring the infinite world of mathematics.